Hello class, welcome to section 12.4, 12.5 again. This is our part 2 of the video. Today we're going to talk about dependent and inclusive events. So we're going to start out with inclusive events. So inclusive means that they are not mutually exclusive, so they can happen at the same time. So an example would be drawing a king or a spade from a deck of cards. It is possible to draw a card that is both a king and a spades, the king of spades. So if that is the case, the way you go ahead and figure it out is you find their individual probabilities. So the probability of being a king plus the probability of being a spade. Then what you would do is you would subtract the probabilities of being both. So the probability of being a king and a spade. So let's just go ahead and look at an example. Example 5. Suppose that 1,400 students, that of 1,400 students, 550 take Spanish, 700 take biology, and 400 take 400 take both Spanish and biology. What is the probability that a student selected at random takes Spanish or biology? Okay, it's not asking for both, so Spanish or biology. So what I would do is, well, how many students take Spanish? 550 take Spanish out of 1,400. Or, so I'm going to add, what's the probability that they take biology? 700 over the total, 1,400. Now I need to go ahead and subtract where both happen. So how many take Spanish and biology? Well, 400 take both, so minus 400 over the total, 1,400. So I would go ahead and add them together. 550 plus 700 minus 400. And when you go ahead and do that, you would get 850 over 1,400. If I reduce this fraction, I would get 17 over 28. And if I divide it out, I get 0.607. Okay. An example of a dependent event. So this is the result of one thing affects another. We've already kind of talked about this. So the same kind of idea is we're still going to be multiplying because same as independent, but now what you do is you would find the probability of the first event and you'd multiply it by the probability of the second event, considering that the first event has already happened. And this is one of those where it's just easier to look at an example. It's less confusing when you look at an example. Okay? So we're drawing 3 cards from a standard deck of cards without replacement. This part's what tells me that it's dependent, so we're not replacing it. Find the probability of drawing a heart, another heart, and a spade in that order. Okay? So I'm going to do heart, heart, and then we're going to draw a spade. Okay? So the probability of getting a heart, well, I think to myself, how many hearts are in the deck? There's 13 out of 52. Then I go ahead, after I go ahead and think about that, I say, well, I have a heart in my hand, so how many hearts are there still in the deck? Well, there's now only going to be 12 hearts, and how many cards are on the deck? There's only going to be 51. Okay. So I have 2 hearts in my hand. So that means how many spades are available? Well, my hearts do not affect my spades, so I still have 13 spades, but there isn't 52 cards in the deck. I have 2 in my hand, so there's only 50. So I would go ahead and multiply all these events. Okay? So if I go ahead and multiply my numerators, I would get 2,028 over, if I multiply my denominators, I get 132,600, and if I divide that out, I would get 0.015. My next example, okay. There are 2,400 subscribers to an internet service provider. Of these, 1,200 own brand A computers, 500 own brand B, and 100 own both A and B. What is the probability of a subscriber selected at random owns either brand A or brand B? Okay, that or reminds me that I'm going to do addition. But here's the thing. It's inclusive because they can own both if they want to. So what I need to do is I need to figure out, well, what's the probability of owning brand A plus the probability of owning brand B, and then subtract the probability of those who own brand A and B. Okay. Probability of owning computer A. There's 1,200 that own those out of my total 2,400. plus my people who own brand B. There's 500 out of my total 2,400. Now I subtract when they own both. There's 100 that own both, so it's 100 over 2,400. Once again, I go ahead and add up my numerators. So I do 1,200 plus 500 minus 100. So I can do that one in my head. 1,200 plus 500 is 1,700. 1,700 minus 100 will give me 1,600 over my 2,400. One thing that's nice with this is my 0, 0 will cancel. I get 16 over 24, which reduces to 2/3, or it is 0.6 repeating. And let's look at example 8. Find the probability of drawing 3 cards of the same suit without replacement. This without replacement is keyword for dependent. So we want of the same suit without replacement. Well, the same suit, well, there's 13 of any suit out of 52. Okay, now if I want to get the same suit again, that means I'm going to get, there's only going to be 12 of those suits out of 51 cards because there was one less card in the deck. And that's going to be 11 out of 50. Well, it says the same suit. It's not telling me which suit, so I have to multiply it by how many options there are to choose a suit. There are 4 suit options: hearts, diamonds, spades, and clubs. So times 4. So when you go ahead and calculate this, you should get 6,864 over 132,600, or this is 0.052%. Okay. This is going to be it for section 12.4 and 12.5. You should be able to finish that 12.4 and 12.5 worksheet. So have a nice day.